Frontier language models are starting to look less like generalists and more like specialists. One model disproves decades-old math conjectures, another finds zero-day vulnerabilities in operating systems, a third writes competitive code better than anyone else. So a natural question emerges. If the best mathematician, the best software engineer, and the best scientific reasoner all live in different companies' models, how do you build a system that acts like all of them at once? That is the puzzle Sakana AI takes on with a family of models they call Fugu, and their answer is to train a language model whose job is not to solve your problem directly, but to figure out which other models should solve it and how they should talk to each other. The setup here matters, because most attempts at multi-model coordination so far have been either very rigid or very shallow. Some systems use hand-designed debate protocols where agents take fixed turns critiquing each other. Others train a lightweight router that looks at your query and picks the single best model. And a whole separate tradition, model merging, tries to blend models at the level of their weights, averaging parameters or stitching layers together. The problem with weight level merging is that it requires access to model internals, which rules out exactly the closed-source frontier models you would most want to combine. The problem with fixed debate protocols is that they cannot adapt to the query. And the problem with simple routing is that it commits to one model up front, losing the ability to combine specializations mid-task. Fugu tries to occupy a middle ground where the coordination pattern itself is learned and can change from query to query. The team releases two variants that sit at different points on the quality latency curve. The lighter one, just called Fugu, is optimized for interactive use and picks a single worker per query, so its latency is roughly a single frontier model call. The heavier one, Fugu-Ultra, composes elaborate multi-agent workflows and is meant for hard problems where you are willing to wait. Let me walk through how each is built, because they use quite different training recipes. Fugu, the lighter variant, is architecturally clever in a way worth pausing on. It uses a pre-trained language model as its backbone, but it does not actually generate any text to make its routing decision. Instead, they attach a small prediction head that takes a hidden state from the backbone and outputs a score for each worker model in the pool. Think of it like reading someone's expression to know what they are about to say, rather than waiting for them to speak. This decision-only design is what makes routing cheap enough for interactive use, because you avoid the expensive auto-regressive decoding loop entirely. To make the backbone's representations actually good for routing without doing full fine-tuning, they use a technique called singular value fine-tuning, which decomposes selected weight matrices and only trains the singular values while keeping the orthogonal parts frozen. That gives you an extremely small trainable parameter footprint. Training Fugu happens in two stages. First, there is supervised fine-tuning on a large collection of verifiable single-step tasks. For each task, they actually run every worker model in the pool multiple times, score how well each did against the ground truth, and turn those scores into a soft probability distribution over workers using a softmax with temperature. Then they train the routing head to match that distribution using a Kullback-Leibler divergence loss. The key subtlety here is using a soft target, rather than just labeling the single best model. When several workers are similarly capable, the soft target teaches the router that either would be a reasonable choice, which produces more robust behavior than forcing a hard pick. After this supervised stage, they switch to evolutionary optimization on end-to-end multi-turn tasks, collected from real coding assistants like Claude Code and Codex. Specifically, they use a variant called separable CMAES, which maintains a mean parameter vector and a diagonal covariance, samples a population of perturbations, evaluates each on end-to-end task success, and updates the mean using a fitness-weighted average of the best candidates. Evolutionary search fits this stage well because the success signal from a full multi-turn trajectory is sparse and noisy, and you cannot easily construct clean per-step ranking labels. Think of the supervised phase as getting you into the right neighborhood of parameter space and the evolutionary phase as refining behavior in ways that only make sense end to end. Fugu-Ultra takes a much more ambitious route. Instead of just picking a worker, it generates a full agentic workflow in natural language. Each workflow is a sequence of steps, and each step names a subtask, assigns it to a worker agent by ID, and specifies an access list saying which previous subtask outputs that worker gets to see. This is powerful because it lets Fugu-Ultra express arbitrary topologies, from simple best-of-n voting to sequential chains to full tree structures where multiple agents attack sub-problems in parallel and a designated aggregator synthesizes their answers. Training this uses reinforcement learning, specifically GRPO, with a simple reward structure. The workflow gets 0 reward if it is malformed, a full reward of 1 if the final answer matches the ground truth, and a partial reward of half if it is well formatted but wrong. GRPO computes advantages by grouping several completions per query and normalizing rewards within that group, which sidesteps the need for a learned value function. A particularly interesting design choice concerns memory in multi-agent function calling. If every agent could see every other agent's tool calls, you get what the authors call orchestration collapse, where the first agent to touch the environment locks all subsequent agents into its trajectory. So within a single workflow, they isolate each agent's function calling history except through the explicit access list. But across workflows in a multi-turn conversation, they share memory so agents do not waste tool calls rediscovering context. That balance between isolation and sharing is subtle but crucial. On results, Fugu-Ultra achieves state-of-the-art on SWE-Bench Pro at 73.7%, roughly 5 to 6 points above the next best frontier model, which the authors note is comparable to an entire generational upgrade. It also tops Terminal Bench 2.1 at 82.1%, GPQA-Diamond at 95.5%, and CharXiv Reasoning at 86.6%. On humanity's last exam, it hits 50%, just edging out Claude Opus 4.8. Perhaps more striking than the aggregate numbers is the qualitative evidence of adaptive strategy. On Terminal Bench, Fugu alternates between GPT 5.5 as a builder and Claude Opus as a debugger, calling in Opus specifically at moments when careful verification pays off. On a game-theoretic question from humanity's last exam, Fugu-Ultra builds a tree with 2 independent attempts at the leaves and Gemini as the aggregator, because Gemini is strongest at niche factual recall. On a mathematical Calabi-Yau question, it uses GPT as the aggregator instead, because the synthesis step requires deriving spectral numbers. This dynamic choice of aggregator role is precisely the flexibility that fixed multi-agent systems lack. On a separate autonomous ML research benchmark called Auto-Research, Fugu-Ultra runs 123 experiments to tune a small GPT training pipeline and beats all 3 frontier baselines on final validation bits per byte, with the advantage becoming most pronounced in the mid to late phase when the search shifts from coarse to fine-tuning. Now for the honest caveats. Fugu's approach fundamentally depends on the worker pool it can access, so its capabilities are bounded by what frontier providers make available and how much you can afford to call them. The evolutionary and reinforcement learning stages both need real end-to-end task environments with reliable reward signals, which is expensive to construct and maintain. The paper reports strong numbers but understandably compares against provider-reported baselines rather than running them under identical harnesses, which is standard but leaves some ambiguity. The routing decisions also depend on how well the training tasks represent deployment tasks, and drift between the two could quietly degrade performance. And while Fugu-Ultra's natural language workflows are expressive, they are also a source of latency and cost, since you are paying for the orchestrator to think plus multiple worker calls per query. Looking forward, the most interesting implication is philosophical. If capability really can be amplified by learning how to compose existing models rather than training bigger ones, then progress in AI stops depending purely on who has the biggest training run. Orchestration becomes a scaling axis, one that is more modular, more accessible, and more responsive to user constraints around privacy, cost, and provider preferences. New frontier models slot in as they appear. Now let's walk through some questions you might have after hearing all of this. First, why does Fugu's lighter variant use hidden states rather than generated text to make its routing decision, and does that not throw away useful information? The reason is speed. Auto-regressive decoding is the expensive part of running a language model, and if all you need is a categorical decision over a small pool of workers, you can extract that from an early hidden state and skip decoding entirely. You do give up the ability to write out chain-of-thought reasoning before deciding, but the empirical results suggest that once the backbone is well-trained through supervised fine-tuning and then evolutionary refinement, the hidden state contains enough signal for good routing. The delegated worker does all the heavy reasoning anyway. Second, why use evolutionary strategies on top of supervised fine-tuning rather than just doing reinforcement learning end-to-end? The issue is that end-to-end multi-turn tasks produce very sparse, noisy reward signals, often just a single binary at the end of a long trajectory. Standard policy gradient methods struggle with that because you need to attribute credit across many decisions from one number. Evolutionary search sidesteps credit assignment entirely by treating the whole parameter vector as a black box and just measuring which perturbations lead to better trajectories on average. Combined with the fact that supervised fine-tuning has already placed you in a good region of parameter space, the evolutionary phase just needs to do local refinement, which it does well and stably. Third, what actually prevents Fugu-Ultra from just collapsing to always calling the single strongest model, especially since that would be a safe baseline? Two things push against that. First, the reward structure only credits correct final answers, and on tasks where different specializations genuinely matter, no single model reliably wins, so the policy has an incentive to diversify. Second, GRPO's group relative advantage means the model is always comparing its current strategy against other completions on the same query, so if a multi-agent workflow beats a single-agent one on that specific query type, the gradient pushes toward the multi-agent version. The paper's qualitative examples of tree topologies with different aggregators for different task types suggest this actually happens in practice. For large-scale recommendation systems, the ideas here map onto several practical challenges. The most direct analog is model routing across a heterogeneous stack. Modern recommender platforms already run dozens of specialized ranking and retrieval models tuned for different content types, user segments, or objectives like engagement versus long-term retention. Fugu's soft target supervised fine-tuning recipe, where you run every candidate model on labeled examples and turn their measured performance into a probability distribution to imitate, is a clean way to train a meta-router that picks the right ranker per request. The decision-only architecture with a lightweight head over hidden states is also directly applicable because ranking systems are latency critical and cannot afford auto-regressive orchestration overhead. You could imagine using it to route between a fast, approximate retrieval model and a more expensive re-rank model based on query features, or to select which of several candidate generators to invoke for a given user. The Fugu-Ultra ideas around adaptive workflows and shared memory are more speculative but suggestive for the agentic recommendation systems that are starting to emerge, where an assistant might invoke a search tool, a recommender, a personalization model, and a summarizer in sequence to answer a shopping or planning query. The intra-workflow isolation combined with cross-workflow shared memory is a nice pattern for these systems because it prevents one component from anchoring all subsequent components while still avoiding wasted redundant retrievals within a session. And the evolutionary optimization approach for sparse end-to-end rewards is well suited to recommender objectives like session satisfaction or downstream conversion, where you have a clean terminal signal but noisy attribution across intermediate ranking decisions.